Check it out now, y'all.
NanoHub U, online instruction.
So what I'd like to do in this lecture is I'd like to try and work out a few examples that I think you'll all be able to understand as a way to illustrate the differences between these two particle wave functions that we discussed in the previous lecture. And so to do that, I'd like to go back to our infinite one-dimensional well problem. So if you recall from week 2 of the course, we've got a well. The width of the well is, or the length of the well is just L, and at L equals +2, the interaction potential energy of the particle in the well goes to infinity. At x equal to -L/2, the interaction potential energy of the well goes to infinity. So if you drop a particle of mass m in this well, and you want to know what the allowed energies are, you have to solve Schrödinger's equation. To make this problem tractable and make it simple, we just define the interaction potential energy to be equal to 0 within the well, and we have boundary conditions now on our wave functions that say that the wave function has to go to 0 at x equals +L/2 and at x equal to -L/2. The reason, of course, it has to go to 0 is because the height of the potential well at those 2 points goes to infinity. So the solutions of Schrödinger's equation are pretty easy to sort out, and you should be able to look back in your notes from week 2 of the course and remind yourself of these results. You recall that we found multiple solutions to Schrödinger's equation. Each solution was labeled by a quantum index n. These quantum index n also gave rise to different eigenfunctions that satisfied the boundary conditions. The eigenfunctions are labeled by the quantum number n so that we can tie the index n to the correct wave function. We also found that there are energy eigenvalues that vary with the appropriate eigenfunction. So again, the energy eigenvalues are subscripted by the quantum number n, and the allowed energy eigenvalues are given in this this column. So the problem that we're going to address now is what happens if we throw two particles, right? Two particles into this well, and let's say each particle has a mass m. What are the allowed what are the appropriate wave functions that these two particles will take on based on these arguments that we've been running through about indistinguishability and distinguishability of the two particles. And so to sort through that problem, I'd like to just pick two quantum states, right? So I'd like to say that one particle we know is in quantum state n equal to 1. The second particle is in quantum state m equal to 4, right? So these two states are completely different from one another. And I'd like to just write down the two particle wave functions for each case. And as you recall, we've got three cases to consider. The first case is if the two particles are distinguishable, one with respect to the other. The second and third cases are if the particles are indistinguishable, so we can't tell the difference between them. We then have the symmetric and the anti-symmetric wave functions that we have to sort through. So I'm just going to write down wave functions. I'll do the first case for distinguishable particles. For distinguishable particles, the appropriate two particle wave function is just the product of the two single particle wave functions. And we can look up these two wave functions because we're specifying their quantum index, n equals 1 and n equals 4, right? the particles are going to be at two different positions inside the well. We'll call one position x1, the other position x2. And if you just go back and look at this table, right, we're going to basically select this wave function and this select and that wave function to write the appropriate two-particle wave function. And so you just write it out. It's pretty straightforward. The two-particle wave function is a product of a cosine times a sine, and the coordinates of the particle 1 is different from the coordinates of particle 2, right? For the case of two indistinguishable non-interacting particles, this would be the case of bosons, right? We would have to use the symmetric wave function, which has got the positive sign. You can see this is the exchange term, and all I've done is I've taken the particle that was at x1 and I've put him in the quantum state n1, but now he's going to be at the position x2, and the particle that was at x2 with quantum number n equal to 4 is now put in the position to have the quantum number n equals 1. So we've just interchanged the two particles. And the appropriate wave function for this case is the sum of the two cases, and I just write it out, right? It's just this rather complicated looking form for the wave function. So this would be the case for two quantum particles that are symmetric under particle exchange. If the wave function is unchanged when the particles are interchanged, that is referred to as a boson. And so in this case, we're imagining these two particles that are dropped in the potential well are bosons. They're not electrons. If the two particles that are dropped into the well are electrons, then we have to use the asymmetric wave function. The asymmetric wave function has this negative sign associated with it. And again, you can see the second term is the exchange term. And what we're basically saying is the two electrons in this problem can't be distinguished one from another, right? So we have to allow the possibility that the electron is in quantum state n1, and that electron could either be at the position x1 or it could be in the quantum state n equals 4 at position x1. So that's what this wave function is saying. We're allowing each electron, each fermion to be in either of the two quantum states. Now, to be technical about this, we have to say that these two particles are non-interacting. The reason we say they're non-interacting, this is just so that we can let u of x equal to 0 inside this potential well. If we took into account the fact that the electrons actually repelled one another, then Schrodinger's equation would have to be modified in an important way, and this discussion would no longer apply. So we in our mind think about this non-interacting situation, right? That's what we call them, non-interacting particles. They're fermions, so they're basically electrons with spin 1/2, but there's no charge associated with these electrons in this example. So it's a hypothetical example that's intended to try to illustrate the implications of the different forms of these wave functions that we've been discussing for the last couple lectures. So once we've written down these wave functions, then we can use them to evaluate some simple questions. And so, like, one simple question you might ask, or you might think of asking is, what's the probability that one of these particles will be at x1 equal to L/3, and the other particle will be at x2 equal to minus L/8, just to pick two positions in this potential well, right? So we're basically asking the question, if you did an experiment and you measured the probability that one of these particles is going to be at L/3, the other particle is going to be over here somewhere at minus L/8. What's the probability that you would measure those two particles in those two positions if you made hundreds and hundreds of measurements of position for these two particles in this well? So to answer that question, we just have to use x1 equal to L/3 and x2 equal to minus L/8 in the wave functions that we've written down for the three cases. So the first case, the case for two distinguishable particles, right? We substitute x1 equal to L/3 in the wave function. We substitute x2 equal to minus L/8 in the wave function. We have to evaluate these cosines and sines, work out the arithmetic, and what we find is that the wave function squared, the two particle wave function squared, is then equal to 1 over L squared times dx1 times dx2. So you tell me how big the increment dx1 is, you tell me how big the increment dx2 is, and you tell me the length of the box that these two particles are confined in, and that then I can tell you what the probability is going to be for this case of two distinguishable particles, of finding one of them at L/3 and the other at minus L/8. So clearly, right, it should be clear that these are just arbitrary positions that I've picked to illustrate this calculation, right? So let's remember that result, okay? Let's remember that result. That's the case for distinguishable particles. What happens if the two particles are bosons, right? That means that they have integer spin. We drop them into this potential well. What's the probability that one would be found at x1 equal to L/3, the other one would be found at x2 equal to minus L/8? Well, we have to substitute in these values for x1 and x2 into the symmetric wave function that we've written down on the previous slide. And so that's what we do here, right? And you have to work out, again, some arithmetic. You have to evaluate the arguments of the cosines and the sines. I work through all this, and at the end of the day, I take psi star psi, right? And I'm using the symmetric version for psi here. And what I find out is I find that the probability that the one particle will be at L1/3, the other one will be at minus L/8. That probability for the case of two bosons is about 3.4 over L squared. So for this particular set of coordinates, right, there's about a factor of 3.4 difference between the probability that you would find the electrons in those two positions if the particles were distinguishable versus this indistinguishable case when they're bosonic particles, right? So the form of the wave function has a profound influence on the probabilities that you're going to find these particles at different points in the quantum well. Right? That's the whole point of the discussion, right? Because once you know the wave function, you should be able to predict all these quantities. You could then check measurements. You could do experiments to check these values. And so, for instance, if you did a measurement, if you didn't know, let's say you didn't know how the particles behaved. You didn't know if they were distinguishable or indistinguishable, right? Well, what you would do is you would devise an experiment to measure, let's say, the probabilities that the particles are at two different positions. You would make the measurements and you would then compare. And from the measurements, you would hopefully be able to tell whether these statistics are being observed experimentally or whether these statistics are being observed experimentally. There's, after all, about a factor of 3.4 difference between them. The third case is the case for indistinguishable particles. So these would be fermions. Because the particles are fermions, we would have to use the asymmetric form for the two-particle wave function. The asymmetric form for the two-particle wave function just has that minus sign right here. And again, what we do is we take the wave function that was written down on the previous slide, we evaluate the wave functions for the particular values x1 and x2 that we've chosen in this example. And what we find is, after we work through the arithmetic, we find out that the square of the asymmetric two-particle wave function, right, is now 0.18 over L squared. So compared to the other two situations, right, if the particles are fermions, the joint probability that we would find one of the fermions at x1 equal to L by 3, the other at x2 equal to minus L by 8, that probability is considerably reduced over the previous two cases that we considered. So, experimentally, you should be able to sort that out if you can do a clever experiment to measure these probabilities of locating the electrons at different points in the well. I just try to flesh this out a little bit more. So here what I do is I actually calculated the wave functions for the three cases that we just considered. So this column here is a plot of the wave functions. The first row this way is for the distinguishable particle case. This is the case for the bosons. So this is the shape of the wave function for the bosons. This is the shape of the wave function for the fermions. And what I'm plotting is I'm plotting x1 and I'm plotting x2. X1 ranges from minus L by 2 to plus L by 2. X2 also ranges from minus L by 2 to plus L by 2. And what I've tried to indicate is the value of x1 equal to L by 3, x2 equal to the value of minus L by 8. Tried to indicate that position by this little box, right? And I systematically tried to locate that box in the same location for all three cases for the wave function. We're not so much interested in the wave function, we're more interested in the square of the wave function because that tells us something that we can measure experimentally. So here's psi star psi for the three cases. And you can see that the probability of locating that electron, or the probability of locating those two particles for any value of x1 and x2, the shape is completely different. So it depends on the form of the wave function that you specify, and that form of the wave function has to match these expectations that we've laid out in the previous two lectures. So that's a very simple example of the implications of the correct form for a two-particle wave function. If you've got the incorrect form for the two-particle wave function, right, you're going to get wrong answers, right? So you have to match the form of the wave function to the problem that you're interested in. That's the key point to take away. The other example I'd like to just briefly mention is what do we do when we put two electrons in the same energy state? And so, for instance, I come back to the case of helium, right? Helium has two electrons in the lowest energy state. One electron has spin up, the other electron has spin down. And except for the spin up and spin down nature of these two electrons, the quantum numbers that these electrons have, the n, the script L, and the m sub L for these two electrons are identical, right? The only reason that you can put these two electrons in this same state is because they have different spin quantum numbers. So how do you write a wave function that might describe these two electrons in this ground state for helium? Right, the electron wave function has to be asymmetric under particle exchange. But there's a problem because the quantum numbers for the two electrons are identical except for the spin. So what you do is you embed the asymmetry under particle exchange into the spin of the electron, and it basically means you have to write a Slater determinant where the spatial part of the wave functions are identical. They have the same quantum numbers, right? But the spin part of the wave functions, which are multiplicative, right, have opposite spins. So again, the first column is electron 1 at position R1. The second column lists the possibilities of electron 2 at position R2. You can see the two possibilities just involve a spin flip, right? One is spin up, the other is spin down. Here, this is spin up, this is spin down. The rows in the Slater determinant are the different states, and the different states in this case are spin up and spin down electrons, right? The quantum numbers for the spatial wave functions are identical. So you're basically embedding the asymmetry under particle exchange in the spin wave functions. So you just have to work out this Slater determinant. You have to multiply along the diagonal and then multiply along the diagonal this way, but include a minus sign. And what you end up with is a two-particle wave function for the 2 electrons in the 1s state of helium that looks something like this, where the asymmetric term that flips sign when the 2 particles are interchanged, right? That asymmetric term contains the spin wave functions of the electrons. So that's a real simple example of how you might use these ideas to start writing down wave functions for electrons in different energy levels for different elements in the periodic table, right? It's just the simplest case that I can think of, and it's easy enough to work out, so it's worth mentioning. What I'd like to end up with is a summary of the lecture. I will not read it to you. You can read it on your own, but it basically tries to make the case that there are 2 types of quantum particles. One type of quantum particle is called a boson, and it has a symmetric wave function under particle exchange. It turns out that these bosons have spin 0 or integer spins, right? That's what distinguishes a boson intrinsically from a fermion. The fermions have to have an antisymmetric wave function under particle exchange, and it turns out that fermions have these odd half-integer spins. So an electron which has spin 1/2 is referred to as a fermion. And so this tries to summarize the distinction between these 2 different types of quantum particles. So this will become a subject we'll discuss more in the next week or 2 of the course. We'll explore the implications of these 2 different classes of quantum particles. So I think that's going to end this discussion. These 2 simple examples that I worked through hopefully give you some insight into what we've been talking about. Certainly by referring back to the infinite square well, the mathematics is infinitely simplified so that you can actually understand the solutions and almost write them down without doing any arithmetic whatsoever. It's just if you understand the principles we've discussed, you should be able to understand the wave functions that we've written down. In the next lecture, I'd just like to very briefly indicate to you how to extend this argument to n-particle wave functions. And it's going to be a very simple lecture, not very long, because we're not going to spend a whole lot of time on it. I just want to make sure that you appreciate these ideas that we've developed by just discussing 2 electrons, right? These ideas are completely general. They can be used when discussing n electrons, and I like to try to make that case in the next lecture. So please come back and listen to that, and we'll discuss the n-particle wave functions for electrons in that particular lecture. So thanks again. You have to think about this a little bit. You have to work through some of these examples, and hopefully, if you understand the big ideas, then you've actually learned something very interesting about how quantum mechanics works. So we'll see you in the next lecture.